Today we're going to cover linear programming, and we're going to go into some detail about how we actually go about solving at least one class of fairly useful, though, optimization problems. So we talked a lot about optimization last time, but now we'll talk about how you actually solve one class, in this case of constrained optimization problems. Before I do that, though, I did want to mention have one last slide from last time. And I mentioned to you at the beginning of class that oftentimes just formulating an optimization problem as an optimization problem was in some ways sufficient to solve it. And so I kind of want to just highlight why that's the case, or in practice why that's the case. So remember our Weber point problem. This is the problem of finding a point that minimizes the sum of distances to other points. It's kind of a hard problem. Actually, if you try to think about it for a while, it's difficult to come up with an algorithm that actually solves that in n dimensions. But nicely enough, you can actually just write these kind of problems sort of very easily in a lot of software packages. So I'm just showing one here. This is a software package called CVXPy. There are a lot of similar ones. But essentially, a lot of software packages let you more or less write down optimization problems as you formulate them mathematically. So this problem is written as x is a CP variable with n dimensions. Our objective is the sum of norms between x and the yi points for all the yi's. And then we set up the problem of minimize f, and then this thing here means there are no constraints, and then we solve it. So this is a library called CVXPy. It's very useful for this reason. And in a lot of cases, especially when the problems are convex, you actually can end up using off-the-shelf software, or at least for reasonably small problems. You can use off-the-shelf software and libraries like this to just solve your problem. So in some sense, the problem is solved because now you know how to write a 5-line Python file that will actually solve it. Of course, this function here, .solve, that's kind of bearing a lot of complexity there, of course. And we won't go into exactly how you solve this one. This one is actually not that easy. It ends up being what's called a second-order cone problem. And those are actually not that, I mean, they're not hard, but they involve a little bit of complexity to solve. So we won't go into it too much. You can use gradient descent on this, by the way, too. It's a subgradient now, so it won't converge great, but you can still do it. But if you want to get a quick solution for a small problem, look into packages like CVXPy. For this next homework, we won't be using them, but maybe for homeworks in the future, we will be using it. And actually, you should use it on the next homework just internally to debug your own solutions. So if you can't figure out why your linear programming solver is working, you should try CVXPy as a way to sort of quickly check those things. And we'll make a mention of that on the homework. Okay, by the way, the next homework will probably be out next Monday or Tuesday. That's the time we're shooting for. And so we'll follow up more on that shortly. All right, so let's talk about linear programming. So what I'm going to do is I'm going to give a quick introduction first of a kind of problem that comes up a lot in linear programming, or kind of how it's introduced a lot of the time. And then I'll talk about the formalism of linear programming. And then finally, I'll spend some time talking about the simplex algorithm, which is a way that we actually can solve linear programs using pretty simple linear algebra operations. So it's a pretty simple algorithm. You can describe it on one slide. It's not too complex, and it lets you actually solve this pretty broad class of problems here. Okay, so let me start off with a simple example. So say that you are operating a large manufacturing factory, and you make tables and chairs. Okay? And each table you sell for $200, and each chair you sell for $100. The tables take 1 unit of metal to make and 3 units of wood to make. And the chairs take 2 units of metal and 1 unit of wood. The factory in stock has 6,000 units of metal and 9,000 units of wood. And so the question is, how many tables and chairs should you make to maximize the profit? So it's actually not, you can work this out by hand without too much difficulty. But let's kind of look at what this problem is actually kind of saying mathematically. So first of all, what are decision variables? This is an example of an optimization problem. Again, it's continuous. Here, we're assuming, even though there's discrete, we're assuming we have enough of these things, like in the thousands, that we're going to treat them as being continuous variables. And so the decision variables will be x1 will correspond to how many tables we make, and x2 corresponds to how many chairs we make. Again, with the possibility of these things being fractional here, because we're talking about having a lot of them. We'll talk about the discrete case next time, actually, when we talk about integer programming. Okay, so each table. So now let's talk about sort of how the constraints in this problem translate into constraints on these variables here. So the first thing we know is we know that each table takes 1 unit of metal and 2 units. Oh, sorry, each table takes 1 unit of metal and each chair takes 2 units of metal, and we have a total 6,000 units of metal. Now what that corresponds to is a linear constraint on the allowable space of chairs and tables we can make, right? Because any point over here will require more than 6,000 units of metal. Right? This line is the line of x1 plus x2 equals 6. So these are in units of thousands. And so any point on this side of the line is feasible, and any point on that side of the line is not feasible. We can't make it because we don't have enough metal to make that many chairs and tables. We'll also assume that we can't make negative chairs or tables, so we're actually also bounded, being both of them has to be positive, and that's now our constraint set of allowable things we can make. We can do the same with the wood side. So we can do the same with wood. We can I think I hopefully got my coloring here right. So each table takes 3 units of wood. Each chair takes 1 unit of wood, and we have 9,000 units of wood. That corresponds to this line here. And we have to satisfy both these constraints, of course, right? We have to both have enough wood and metal. And so now our allowable space of tables and chairs is this blue region here. And that describes the allowable space we have in terms of how many chairs and tables we can make. Now, the last question is, how do we actually choose a point in that space to operate at? And what we have there is that our profit is determined as 2, or in this case 200, I'm just scaling them to be a little bit more nicer, the numbers here, 2 times x1 plus x2, because we make $200 from a table and $100 from a chair. And so the question is, where in this space should we should we situate ourselves such that we maximize along this vector, right? And the way we do it is we just sort of look at this vector here. We kind of pick the point that's perpendicular to that vector, or pick the lines perpendicular to that vector, and pick the farthest point kind of along that line, right? And that in this case would be this point right here. That's the number of chairs and tables we should make. So we should make 2.4 thousand tables and 1.8 thousand chairs. That maximizes our profit out of the allowable constraints. Is there any questions there? Okay, now this was a very simple example, but it turns out, and it's sort of one that kind of doesn't really seem like a very AI flavored, right? It seems more kind of either math class or sort of operations research flavored. But it turns out that within AI, and really I should say, within a huge range of fields, there are hundreds of applications of linear programming. So to name a few, finding the optimal strategy in a zero-sum 2-player game, that ends up being a linear program. So we'll talk a lot more about game theory later. And I'm not sure if we cover it in this respect, but essentially, a certain class of games, at least, are solvable tractably by linear programming. Also, things that you might seem kind of far afield, like probabilistic models. It turns out you can actually formulate finding the most likely assignment in probabilistic models. You can formulate that as a linear program and solve it like that. Also, things like Markov decision processes, MDPs. They are not typically done this way, but they can also be formulated as a linear program and solved that way. Some very sort of classical computer science algorithms like MinCut and MaxFlow, actually the best known algorithms for solving these in terms of complexity are formulating them as a linear program and then solving them with a specific algorithm that's very fancy, not the one that we're going to talk about here. But they actually theoretically are, both in theory and in practice, are incredibly powerful techniques for solving these kinds of problems. And lastly, I won't even come close to covering this all, but there are just a huge wealth of applications that rely on linear programming kind of as a fundamental operation to solve the problems. Okay. All right, any questions now? Okay. Really? You sure? Who here has seen linear programming before? Okay. Oh, wow, almost everyone. That's fantastic. You don't usually get that in an AI class, so that's great. Who here has used the simplex method before? When you used it, did you use it as like the Tableau method or just as just linear algebra? Who said did the Tableau? And who didn't do Tableau? Okay, so there's going to be a few people that, well, I think everyone will learn something, hopefully. Okay, so let's talk about linear programming then. So the first thing I'm going to do is I'm going to take this problem here, and I'm just going to, I won't even bother writing this down again, because I'm going to write the more general form in a second. But I want to emphasize that what we're really doing here is we're framing an optimization problem, right? So this is exactly the kind of form we talked about last time in class. Here we're maximizing, we're not minimizing, but you can also just minimize by maximizing the negative, so all kind of the same thing. We're maximizing 2x1 plus x2. So that term that we're maximizing is our objective function. And these linear inequalities here are our constraints, right? So those are the constraints we have to satisfy. They're all linear, and our objective is also linear. And what makes it a linear program, in fact, is that both the objective and the constraints are all, in fact, linear, right? And we can generalize this. This is sort of a very simple form here. It's also kind of intuitive, and it's actually good because you can kind of see the variables individually. But if you have hundreds of variables, it isn't very practical to write it out like this. So what we can do is write these problems in a more kind of compact form that uses linear algebra notation. And we're going to write these as maximize. Again, the operation we're doing is a maximization. That's the operation we're carrying out. Some vector C transpose, some inner product between some vector C and our variables x, subject to gx is less than or equal to h. Right? And that g here is so C is a vector that's n-dimensional. I should probably write this all down. So x is going to be in Rn. C is also then in Rn. G is a matrix, which is M by N. And then, of course, to make the products work out here, H has to be a vector in Rm. All right. And here, inequality means element-wise inequality. So when I say Gx less than or equal to H, what I really mean is that if I write G, by its rows, say this is G1 transpose, G2 transpose, et cetera. So the rows of G. What I mean really here is that Gi transpose X, where Gi is the ith row of G, so it's a n-dimensional row vector, that is less than or equal to Hi for all I. For all I equals from 1 to m, just to be perfectly clear. Okay? So that's what I mean when I write this in inequality form here. And very importantly now, this is a convex optimization problem, right? So it isn't very hard to show. It's actually really easy to show. I think I showed something very similar last time, that this set here, this constraint set is convex. So I take 2 points that satisfy this, and I look at the line between them. All those points also satisfy that. And this objective term is also convex, right? Because it's actually, in fact, linear. So it's convex and concave. It's affine. But it's also convex. So I can write my problem, like I had before, in this form. And this is a matter of sort of setting up the entries of the matrix. If I have a problem like this, I can write it like this, where C is the coefficients on the objective there. G are essentially the matrix of coefficients on the inequality constraints. And H is that. I have 2 more rows here, because I also have a row for the positivity constraint of each variable there. Okay, so let me now talk a little bit about the geometry of these problems. So let's think about a single row here in our constraint matrix. So let's think about a single term here. Gi transpose x less than or equal to h. What this is what's called a half space constraint. So it essentially divides Rn into 2 regions, one that's bigger than h, one that's less than h, and says our point has to lie on one side of this. Right? And in fact, the length, you can actually compute that from the actual line you can compute from those 2 terms. But really just think of this as G as a vector kind of pointing perpendicular to that constraint plane. And that's the constraint says I have to lie on this side of the constraint. Now, when I take many of these together, so now multiple half space constraints, this is what I, in fact, have in our program here. I look at a lot of them. Now I'm talking about an intersection of multiple half spaces, right? Because this inequality means it has to satisfy all of them. So I'm talking about really an intersection. I have to lie in the intersection of all those half planes. And the set of all these things is what's called a polytope. Okay? And so linear programming really is just equivalent to the following. We're just trying to minimize or maximize our, we're trying to maximize some direction, right? So C transpose X is some direction in this space. We're trying to maximize some direction subject to the constraint that we have to lie inside this polytope. Right? So you can think of a vector C pointing in some direction there, and we have to pick the point inside that polytope that maximizes X in that direction, or maximizes the function C transpose X, which is the inner product of X in that direction. And one point that was actually made last time, but which is not true in general of convex optimization even, is whether or not the solutions have to lie on a corner of this set, or can they lie in the interior? And so for general convex optimization, they can lie, of course, in the interior, right? Because we can have a point where the function just has this natural minimum right in the middle of that. But for linear programs, the objective is always kind of purely increasing in one direction, right? And so for there, you never have kind of a bowl to your function. It just keeps going on flat in one direction. And so in this case, we are actually going to have a solution that always occurs at one of the corners in this polytope. It can occur, so if C is exactly the same, the same as G1, then actually all the points on G1 have the same value there. So that the entire line there is a solution. But in general, so would a corner. A corner would also be a solution. And in general, the corner points are the solutions. So really, linear programming is about finding a corner or a vertex in the polytope that maximizes our objective. Okay? So this raises a nice question. How many corners are there in a polytope? All right, so I'll open this poll in a second. Let me open it up. Let's see. Oops. All right, so the question is, let me just, oops, I hadn't refreshed. Oh, I think I must have made them in the wrong class. Did I? Oh. That's the problem with having too many classes. Shoot. Okay. You can't like clone across classes, can you? Oh, okay. Let me create this. All right, I'm just gonna add the responses. Then I'm just gonna create like a dummy poll with the responses 1, 2, 3, and 4, and you have to know what they're the ones on this slide or this slide. So sorry about that. I'm going. So think about this while I create the poll. How many things there can be? All right. So I should delete those other ones too from the other class. Can you? Yeah, you can see it still. Okay, good. Yeah, these are all defined by linear inequalities. All right, can you see it now? Did it just show up? Okay, let me create the other one too in a second. So, what was that? Yeah. All right, let me also clone this. Oops. Okay, so is it can everyone vote? Is it people are voting, right? I see 51 votes so far, so hurry up and pick one. All right, 20 more seconds. All right, I'm closing it in 5, 4, 3, 2, 1. All right, let's see what people said. Okay, so that's interesting actually. So people are inversely proportional to how correct they are. So the answer is 4. The answer is n to the n. But 2 to the n is a reasonable number, a guess as well. So actually n to the n I won't prove. I'll prove at least 2 to the n. N to the n, it's actually not quite that. It's like there are k equalities. It's k to the n over 2 is the actual answer. Okay, so why is this the case? So this is actually what makes linear programming so interesting in some sense, is that a simple number of inequalities can describe a really complex set. So the case to think about, or one case to think about here, is the case where you have these constraints, say -1 and 1. All right? So think about that at n dimensions for all I, for I equals 1 to n here. Okay? So it shouldn't be too hard to convince yourself that every possible combination of 1 and -1 is a corner of that polytope, right? Because there's going to be some set of faces that actually does intersect at the point x1 equals 1, x2 equals -1, x3 equals 1, etc. for all possible combinations of -1 and 1. And that, in fact, does enumerate, I mean, that would be, there are 2 to the n different possibilities there, right? And each of those is a corner, is a corner point on that polytope. Okay? So it actually is bigger than that. There's I forget the name. I was looking at this last night. The name of it is like the cyclic polytope, which is defined by these curves. And you can construct a polytope that has actually more than this. So if there are k inequalities, you can actually have k to the floor of n over 2 different corners, but I won't worry about that. It's a very complex polytope that gets you that. So the easy one gets you 2 to the n, and the hard one gets you some k. So if you have actually only n minus 1 can you have, but then you can get something pretty high there. So the answers were 3 and 4. But this really does show, and sometimes the power of linear programming, because in fact we are talking about enumerating a very complex set, but doing and finding a point in that complex set, right? Because we know the solution is going to be at a corner, but doing so in a very compact way. Is there a question there?
Yeah. Like, is true that a corner is actually when we take some of the inequalities and fed them to inequalities?
Yes, it is. That is what a corner is.
So then the number of subsets of the inequalities is actually equal to n.
The number,
If you have n inequalities, the number of subsets of those inequalities you can choose is to use n.
well, no. So if you have n of them, then you can pick. So you can pick any n, choose k to be active, and so it's actually a combinatorial. And so that's why you can get at the most n, choose n over 2, which is kind of like n to the n.
Okay.
What's hard, though, well, I'll get to why that's not trivial to do, though, is actually it took a while for them to figure out that was the upper bound. That was like in the 50s, so this is not an easy thing that was proved many years ago. That was fairly recent. I mean, speaking in terms of math, right? Okay, so, all right, so that's one question. So now let me actually ask you the flip side. What do people think about this one? So if I have order n, if I have now a polytope in n dimensions with order n corners, how many faces can I have? How many inequalities do I need to describe that? So it could be like log n, right? We know that. I'm not giving that as an option. So let me open up that poll. So same question, but now how many inequalities are there? In fact, I'm going to just move this. Oh. I'm going to look at it myself for a while. Okay. Yeah. No, I mean, no, the minimum is, you already know is like log something. This is in the worst case, how many, what would you need to describe it? In general, how many do you need to describe them? Okay, so we have 70 votes so far. People, 30 more seconds. Okay, 10 more seconds. I don't know if I'm counting actually accurately there. Sure, I'm not actually. All right, and closing. Now, everyone? All right. Okay. People think it's order n. So can someone that actually voted order n, can someone explain that answer? Any volunteers? No one? Someone can be brave. Come on. Yeah. So you're thinking, look, because we sort of saw that there was this thing that could have n to the n. Take the log of that. That's n log n. So approximately n, order n. Okay. Anyone else? I should have put that as an option, actually, n log n. That would have been good. Anyone else? Okay. So the answer, again, is 4. It's n to the n also. Again, I won't prove that one. That one's hard to come up with. But the example here is actually the opposite of this. So this is actually what's called an L infinity ball because it looks like, well, I won't actually give that. But this looks like this, right? This is sort of, this constraint is all the points like this. So the one to think of for the other case here is what's called the L1 ball. So that's this point. And so the points that are at corners of that polytope are all the points along each axis where all the other points are 0 and that one axis has a point 1. All right, and you should also be able to convince yourself when you do this that sort of all this is 2D, so they both have 4 faces and 4 points. But in higher dimensions, the number of points here will only grow like 2 to the n. But you will need an exponential number of faces to actually have each face here, 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 etc. Right? So that's the one that has 2n points, and it has 2 to the n different inequalities that are required to describe it in inequality form. So it's really interesting here. There's actually a perfect duality between these two things. And you can come up with polytopes that are easily described in terms of their vertices, but very complex in terms of their inequalities or faces, and vice versa. So you can actually do both. And that's kind of the fun of linear programming. Though I should say that linear programming really focuses on the case where you're describing them as these inequalities here. You want to use a different formulation if you describe them in terms of their vertices, or a slightly different formulation if you describe them in terms of their vertices, because obviously it's not very useful to do it this way. Is the question over there? Actually, yeah. Yeah, so the example we have here is this example. So I'm going to give the two-dimensional example of this. So this one, it's the points that I have, the collection of corner points, are all the points. Maybe I'll just write it like this. They're all the points. X, whatever, x1 is all zeros, but a 1 in one column. And similarly, you have one that is all zeros and a -1 in that entry. And then you have this just for all of them. So you have 1, 0, 0, 0, -1, 0, 0, 0, etc. for all those combinations. And it's a little less easy to show in this case, or think about. But if you think about it, for every, what this sort of does is this sort of describes like a diamond-shaped thing in n-dimensional space, right? And you need an exponential 2 to the n different faces to describe all possible sort of combinations that pass through, these this set of points and this set of points. Like basically picking one. So the faces you need are to describe. You pick basically for each of these. You pick one is 1 and one that's -1, and you find the face that passes through all those points, and you have to do that for all possible combinations of being +1 or -1 for all the points. So that's the 2 to the n example of this case. And so it's really interesting, right? Because this geometry is not at all what we think of when we think of, in two-dimensional space, it's the same. They just look like this, right? So they both have 4 faces and 4 points. But in n-dimensional space, they're very, very different beasts, these two things. Yeah?
The complexity would also depend on what dimension it is, right? Not just the number of corners.
So n is the dimensionality of the space. So this is for in the question, it's always in n-dimensional space. And order n points, what's the number of inequalities you need?
So again,
yeah.
There are 2 answers, or just?
There's 2 answers again. So the 4th one's actually right, but 2 to the n is a reasonable answer too. I'm only showing you 2 to the n, but it actually is again n to the n over 2. Yeah. Okay. So that's kind of fun, right? The geometry is really much more complex than you might think about. The next thing I'll say is these things are potentially both infeasible or unbounded, right? So I'm describing, in this picture I have kind of a nice closed polygon. So wherever direction or polytope, I should be specific about that. So I have a nice closed polytope. So whatever direction I optimize in, I both will have a solution and it will be a finite solution, right? But you can of course have the cases too where these things are either infeasible. So maybe you have, 3 planes like this, and in each case, the half space is this side and this side and this side, and there's no point that lies, on the other direction where the arrows are pointing of all those half planes, right? That's an empty set. So that problem, if you try to solve that linear program, that would be an infeasible problem. Similarly, you can actually have the case where you have an unbounded polytope. Right? There's nothing constraining this to be a closed set. It can go off forever. And if you're optimizing in that direction, you can have an infinitely good solution, which is great if you're making chairs and tables and you can actually make an infinite number, but probably you actually just misspecified your problem because you probably can't actually make infinite money by solving a linear program, unfortunately. All right, any questions?
Is there a very short proof about why the optimum happens at the corner?
Yes, I mean think about this, right? Pick any. Well, again, this is sort of more. Yes, there is. I mean, the short proof here is suppose the solution occurred in an interior point, right? The optimization is in some direction, so you have to be optimizing in some direction. So it's this direction. So there's a way you can go that actually makes you get better. And that happens even if you're on an edge too. So if you're on an edge, unless the direction is exactly on that edge, in which case the nearest corner also is in a solution, then there's always going to be a direction you can go, a small step you can take to improve your cost. Right? So the only place you can kind of stop improving is at a corner.
So basically for bounded polytopes, you just have to specify these vertices and say take the mean or the max.
I see. Okay, that's a great question, actually. Yeah. That's a great question, actually. Why couldn't you just enumerate all possible corners and solve it that way? Well, again, you have 2 to the n possible corners, right? So this is a really simple program where I have bounds and just 0 and 1 bounds on these things. This would be a really simple linear program to write. Here I would just have 2 to the n constraints. And that's actually really easy one to solve, too. So this one isn't that interesting. But if you were to check all of them, you would be checking out 2 to the n possible solutions. So you don't want to do that. That's a really bad algorithm.
You walk along the edge.
Right. So the question is, can you walk along the edge the right direction? And that is exactly what the simplex algorithm does, in fact. So we'll talk about that. So that's good, actually. I mean, George Danzig had to think a long time to come up with that. So that's actually fantastic that you had that idea. It was a really monumental algorithm when it first came out in the early days. But it is that simple. You just walk along edges. We'll get to that in a moment. Before I do, I want to actually describe a different form for these polytopes and for linear programs, because we're actually not going to use this form. We're going to use a slightly different form to talk about our linear programs. And it's a little less intuitive, the form I should add, but I'll give us some examples which hopefully make it a little bit more intuitive. This is something called standard form. So standard form programs are the following. There I had, maximize x. By convention, in inequality form, you say maximize, and in equality form, you say minimize, or standard form, you say minimize. But that can be flipped because it's linear. You just negate the objective, and you can do either one. So this is just convention. So standard form problem, it says to minimize over x, again, C transpose x. If you're converting between the two, you have to negate one to make it a minimization instead of maximization. Subject to ax being equal to b and x greater than 0. Where here, again, x is a vector in Rn, These sizes are not the same sizes as that one. I'm just going to use M and N to describe the size of matrices, period. But they're actually different in the sizes of those matrices up there in inequality form. A is a matrix, which is M by N, and B is a vector in Rm. Okay. So this is a little less intuitive, this form, because now we don't really have any inequality constraints except for the greater than or equal to 0 constraints, right? So it seems a lot less, how does that correspond to this interior of this polytope? It seems much less obvious. Because this is sort of a line, right? These are kind of subsets of the space that have to lie on this equality exactly. So how does that correspond to the same thing? And it looks very different. It's a little less intuitive, but actually it's very easy to convert between these two forms. And the way this is done, or at least in the simplest case, the way this is done is something called slack variables. So if we have some constraint, gi transpose x less or equal to hi, if we want to represent that same constraint in standard form, all we do is we actually add another variable, which I'm going to call si, and si has to be greater than or equal to 0. And we add the constraint that gi transpose x plus si is equal to hi. Right? And that will be possible if and only if there's some si greater than 0 that satisfies this. So this holds if and only if this holds. Right? So that's how you convert between these two. Another little minor things here. If you have variables, these variables by definition here have to all be positive. So if you have variables that are not positive, you have to add a variable for the positive part of the original variable and one for the negative part of the original variable. That's a total pain. No one actually does that in how they're solved in the back end. But mathematically, if you want to be pedantic about it, you do have to make them all positive, so you have to add these separate parts. We won't deal with that, so don't worry about that. Just know that there is a way to convert between these two forms. This is also nice because this way you actually can represent equalities constraints exactly. Those are also convex constraints. And you can do it in inequality form by having one greater than and one less than for the same constraint, but that's kind of hacky again. You wouldn't want to solve it that way numerically. So this form's a little bit nicer for numerical solutions. Okay. So let's talk about then, give an example about how we convert to standard form. So here's our original problem. That's a problem which we're writing in inequality form. That was a problem of chairs and tables. We had two inequality constraints plus the non-negativity constraint. And so the way we write that in standard form is, first of all, we flip the objective, right? So we now have -1 and -2 and -1 as the coefficients on the objective because we're minimizing instead of maximizing now. Again, that's just convention. Don't worry about that too much. But then our inequalities all become equalities with an additional variable here. So x3 is now the slack variable for that first inequality. It becomes an equality, and we have the constraint that x3 is greater than 0. Similarly, x4 becomes the slack variable for the second constraint, and we have it equal to 6. We have it equal to 6, and then x4 is greater than 0. And if you want to write now down the actual form, the C, A, and B matrices would be the following. Yeah?
Does I guess, most of that matrix always form like a diagonal with the addition of the slack variables cube?
Yeah, so if you add slack variables and you only have additional slack variables of that form, then yes, you'd have the identity block there because you'd be adding 1 to each inequality. But you can also, you can put them in a different order if you want, right? So yes, they do, but only if you're only adding slack variables. If you have to do the splits between positive and negative parts, then it doesn't happen anymore. So it happens both ways. Okay. So now we're going to start getting a little bit more notationally complex, but hopefully it won't be too bad. Because I'm going to start doing things like subsetting into entries of this. So let me talk, but to motivate this all, let me talk about how we go about finding corners of the polytope in n dimensions. So, suppose we have some polytope described in standard form. So again, the polytope here, I should say, to be a little clear, the polytope is defined by the ax equals b and x greater than 0. That's the polytope. And then the objective is the C term. So when I say we have a polytope, I really mean we have an A and a B matrix, or an A matrix and a B vector, plus the greater than 0 constraints. So the question is, but think of it geometrically the exact same way as you thought of it before. So think of it just in terms of half spaces that you just then added some slack variables to make into this standard form. Okay. So to find solutions, to find corner points on this, there are in the A matrix is M by N, and the only thing that makes sense for an A matrix is to be a wide matrix, right? Because there has to be underdetermined set of equations, so there can be more than one solution. If there's only one solution, it's really boring. You just invert it to find the solution. So it's only interesting linear programs when N is bigger than M. So you have more, in standard form, you'll have more variables than equalities. And the question is, how do I find sort of my corner points here on my polytope in this form? The way you do it is you take a subset of the columns of A, and you take, in particular, M columns of A. So this is saying, at a corner, and actually this was sort of alluded to before, but at a corner in your polytope, we know that exactly n constraints, what n's the dimensionality, have to be active here. And in the standard form polytope, that corresponds to essentially picking from this thing m columns of my matrix that I'm going to sort of treat as the active constraints, the ones that actually hold with equality. All right. So the way I write that, let me just erase a few things that aren't very important. So I'm going to write A like this by its columns. I'm going to refer to the columns of A as A1, A2, A3, all the way up to AN. There are n of them. And A subscript I, that's actually an I script I, here I is going to be some subset of 1 to n with m entries. So script I, the size of it is m. So when I say A subscript I, what I mean is I'm selecting a column, or I'm selecting m columns of my A matrix. So this is going to be a square matrix where I've subselected m columns of my matrix. I'll also use this same notation to write things like x tilde I. That means just the subset of those m entries of x corresponding to the entries in I. So script I is a set, and I'll use that set to index either into the entries of x or the columns of A. It's important it's the columns, not the rows. It's the columns of A. So what I do to find potential corners of my polytope is I pick some subset. I pick some subset AI, and then I solve the equation AI xi equals b. This is now a square equation. This is an m by m system of equations, so I can solve it. We'll assume you actually are, as long as A has some properties like full row rank, in the simplex algorithm you will only find solutions that are in fact invertible here. So we're just going to assume that these subsets are invertible. These matrices are invertible. So what you would get is you get x tilde equals xi equals AI inverse B. And that gives you your solution to A. And here's sort of the important point. The corners of the polytope, the vertices of the polytope, are all those solutions to these equations for all possible subsets I, where this solution is greater than 0. Okay? So X is a corner, basically X tilde, but really all the other things in X are 0 except for the I keep saying tilde, X subscript I. X script I, all the entries besides I are 0. And that is a solution, or that's a corner, if it's bigger than 0. So let me show you what I mean by that, because it's much easier to show this kind of visually. Of a few things here. So here is, I have my polytope I've defined for my problem here. And I'm going to select some subset here. So I'm selecting here the third and fourth columns. So AI would be, this in this case, the identity matrix here. And so to form XI, I just take AI inverse times B, which is the identity inverse times this, which is just that. Okay? And now I set X to be the vector that's 0 everywhere else except for those two entries. And if I plot that on my original plot, and again, my plot only shows x1 and x2, that would just, those two are both 0, so that's just this point right here on my polytope. Okay.
Similarly for the other.
Yeah, and similarly for all the others. So let's try another one. Let's look at these two columns. You have to only pick 2 columns, remember. Here, this I is 1 and 4. If I form the same thing, I get these columns of I inverted times B equals this. So we know that X is equal to that thing. So again, X1 is equal to 3, X4 is equal to 3, the rest are equal to 0. And that corresponds to this point right here in my space. Okay. Now, the interesting thing is, of course, not every point will have X bigger than 0 for the solution, right? So let's pick another one here. Let's pick those two, do the same thing, form the inverse, and what we actually get is a negative point here. So if I look at where this point lies in the space, this point actually lies here. This point lies here. So the subsets, those are all intersections of n, or of m, of these planes, right? Where we know it's like an m by m equation, so each subset is an intersection of m of these different planes. But not all of those actually lie on a corner of the polytope. The ones that do are exactly the ones where the solution is always bigger than 0. And so this is a really nice form for being able to easily enumerate how these corners are formed in this polytope. This is, and sort of the ease of doing this is one reason why standard form is very popular for algorithms that manipulate linear programming problems. Okay. Any questions?
Why did you mark less than?
Well, yeah.
Be greater than 0, that's just saying that your slack variable should be positive.
Yeah, so essentially, yes, the slack variables have to be positive. And so what's happening essentially for the ones where one of them is negative means the slack variable is negative, means you are on the wrong side of one of the equalities. And so therefore, it's actually not a corner in the polytope. It's just an intersection of some of these inequalities, but not actually a solution, not actually a potential solution, because it doesn't satisfy the constraints. So that's the intuition there, is that the solution here has the slack variable, in other words, x3, being negative, which basically means you're, and what that means here is that you're violating one of these inequalities. Yeah?
So what happens if we choose the index set as the actual variables and not having any of these?
So in this case, that actually is the solution. You can do that, that's fine. What that means is all your variables, essentially, none of them are going to be equal to 0 in the solution. They're all positive, right? Or if one were negative, then it wouldn't be a solution, right? If any were negative, it wouldn't be a solution. Oh, absolutely, yeah. So I mean, yes, they absolutely can. there's no easy way to guarantee you're going to find a solution. These ones are kind of easy, this because like for example, I know that 0, 0 is a solution point here, but when I take a general polytope and transform it into a standard form, it is by no means always easy to find a point that satisfies this. In fact, finding a point that is definitely feasible in this way is actually oftentimes requires solving its own linear program to do that. So we'll kind of, I actually won't mention that too much. We might talk about that a little bit on the homework, actually. But it is not always easy to find a point that satisfies this, that is essentially a feasible point for this polytope.
So how do you choose an index set which kind of, there's like some guarantee of getting
So it's very hard to give any general procedure for that. For a lot of specific cases of problems of linear programs, you can come up with a rule that's very easily is guaranteed to give you a feasible set or a good set in some sense, a good index set. But in general, there's very little you can say about that. Because I mean, as a linear program, I could just swap these entries. There's no real, I mean, I created it from these Slack variables, but I didn't have like, if you just saw this, you wouldn't know I did that, right? I could permute all the rows and shuffle them all about, and you can do whatever you want here. So it's not trivial. Yeah. All right. So the time I have left, I want to now talk about the simplex algorithm. And this is going to be a little bit quick and a little bit dense here. And so really, the slides here are meant to be a reference for this. So if it is confusing when you're implementing it on your homework, go back to the slides and see if you can make sense of this. They're intentionally a little bit dense, so you can follow along with it as a complete derivation of the algorithm, not just as sort of for me to show in class. I'll try to go through as much as possible, but it will be a bit dense. So if it seems a bit rushed, don't worry. The actual final algorithm is very simple. It's 10 lines of code maybe, which is really impressive. But you do have to know that there's a little bit of math behind it. However, the nice thing is that intuitively, it's actually a really simple algorithm. The idea of the simplex algorithm is exactly what Jonathan mentioned before. It is really just a matter of taking my polytope and walking along the corners of that polytope from corner to corner in the directions that improve my cost. So if I have a polytope like this, and I start off at that point on the left there, every step I'm taking is actually improving my cost, right? And I end up then at the optimal point. And it turns out that is, even when there are potentially exponentially, an exponentially large number of corners, it is often the case that when you walk from one to the other, you have to encounter much fewer than all of them, essentially. So even though actually the simplex in the worst case also is exponential, so you can come up with these really, really nasty cases where you have to sort of take all possible steps here. In general, it's incredibly fast, and on the order of usually n steps or something like that, or some multiple of n. And so these things work very well in practice. Okay. However, they are not technically polynomial time. For those that are interested, they're actually and there's a whole other class of algorithms that actually are polynomial time, but it is not the simplex. Okay, so I have now 4 slides that derive the simplex algorithm. Now, when people, and I asked this at the beginning of the class, but when people are often taught the simplex algorithm, they're taught kind of procedurally what you do using this method called the tableau. And I have to say, I really hate the tableau because I think it conveys no intuition about what you're actually doing to solve the problem or why you're making these steps to solve this problem. So I'm not going to even mention the tableau here other than in passing right now. I'm going to derive what the simplex algorithm is doing from a purely linear algebra standpoint. So we're going to talk about why you want to adjust certain things the way you do and what the consequences of that are. So let me start out by saying, and actually this isn't really, so it's really just 3 slides is the dense part of this algorithm. But the setting here is, suppose we are optimizing a linear program and we have some initial feasible solution. So I'm going to suppose that we have an initial feasible point. If you don't have that, you can relax that by essentially formulating another problem that will give you a feasible point at the end and which itself has an obvious feasible point to start with. But we're not going to do that today. So I'm going to assume we have a feasible point. Now, importantly, when I say we have a feasible point, what I actually mean is we have an index set. We have some index set such that when I solve this equation, it returns a positive solution. That's what a feasible point really means here. So I'm defining it not in terms of the point itself, but in terms of the index that leads to that point. Okay? And in fact, what the simplex will actually do is the simplex will actually operate mainly on that index set. It'll be adding and subtracting things from that index set, which is implicitly actually taking steps in the actual variable itself. But the main operations are going to be adding and removing elements from this index. OK, so I have some initial point. I'll call it x. And we know that x sub I, x subscript I, is given by that equation. The rest of the values in x are 0. Right? That's my first feasible point. Now, I would like to change that point in order to get a better objective value. That's my goal of linear programming, right? I want to minimize my objective. So how do I change that point? So let's talk about a few things. Suppose, first, I'll go through the first point of how I change it. Suppose I want to set some xj to be equal to some positive number alpha for j not in my index. Right? That would be an adjustment to x. I'm adjusting x to add some new element, hopefully with the hope of decreasing the objective value. But I can't just add a point to this, because when I do, the solution will no longer satisfy the equalities, right? Because we know that this is satisfied. X already equals b. So I can't just add alpha, and it really would be alpha plus aj, because I'd be adding alpha times this column of a. This is not going to equal b. So I can't just go ahead and increase some new coordinate in my solution. So when I increase, the upshot is when I increase a coordinate, I have to somehow adjust my other variables as well. In other words, I have to find some d script I, such that I'm going to adjust the other variables by d script I. And that, changing, so what I'm going to do is I'm going to adjust this by that. And I'm also going to adjust xi to be equal to xi plus alpha d script I. And I'm going to require that when I do that these still satisfy the equality constraints. So how does that work? Well, let me set it up so that it does work. What we need is for a times xi plus alpha di to be equal, plus alpha aj. This has to equal b. So if I do that, if that condition holds, then my equality constraints will still hold after I do this. So let's just simplify this. This means that I'm going to put the di on the left-hand side here. Alpha a di is equal to b minus a xi minus alpha aj. Everyone follows why the aj came there, right? So I'm increasing xi, and so that means this whole term would have an extra alpha aj, because aj is the jth column of a. So I have to have this hold when I do this. But fortunately, these terms cancel, because we know that in the current solution, a xi equals b. And so these terms go away. And so now I actually know what my d term has to be, but I have to make it in order to satisfy this when I adjust xj. In other words, di, the alphas also cancel here. And so in other words, di is going to be negative alpha I inverse aj. So in other words, if I'm going to increase, if I'm going to take this step here, xj is going to get the value of alpha. Currently it's 0 right now. And xi is going to get the value of xi plus alpha di. This is the formula for di. So that's how I make adjustments. Now, the next question is it a good idea to do this adjustment or not? Like, should I actually increase xj and therefore, and in doing so, change all my other xi's in this manner? Maybe. So the second question is, do I even want to do this adjustment? So what happens to my objective function if I take this step here? So my objective before was cx. Actually, only the xi's were positive, so you could have subscripts here. You could have this. That was my objective before. And if I take a step and set xj to be equal to alpha, adjust these things as needed, then this would become, my objective would sort of change. It would be the old objective too, plus alpha times cj, that's the contribution I get from adding a little bit to xj, plus c tilde I transpose, or sorry, I keep saying tilde, c script I di. This is the change in objective I get from this part here, right? Because I'm also changing the other variables, the xi variables, and so I get a change in my objective from those as well. Okay, so that's how my objective changes if I'm to increase xj by a little bit. And so the question now is, should I do it or not? Well, just sort of being a little bit, writing things a little bit more in sort of, this is how it's typically written. I'm basically going to take this thing and think about whether that is a good thing to actually go ahead and change. So I'm going to compute this thing called c bar. And c bar is the change the objective would have if I were to actually go ahead and make this step. And so c bar is just going to be basically this thing right here. It's going to be, or I shouldn't say assigned, it's just equal to Cj. This is how much the objective will change if I take this step, minus C, well, I'll say plus C transpose di, which equals Cj minus Ci transpose Ai inverse Aj. That's just my definition of di there. So here's sort of the key, is that I can compute all those things for all j's, right? Compute this c bar j for all j's. And if any of them are negative, then I know that I can take a step in that direction and get this change in my objective. In other words, I can decrease my objective while increasing one of my coefficients, xj. So if at least one Cj is negative, then we can make progress and we can take a step in that direction. If they're all positive, then nicely enough, we're actually done. We know there's no adjustment we can make to any of our variables that will cause the objective to decrease. And so we're actually at our solution. And the last question now. So this is the last math slide that we have. Last question is, how big of a step do we take? What do I pick for my value of alpha? In fact, you don't even actually end up seeing alpha in the final simplex algorithm, but that's sort of conceptually what it's doing. So there's a couple cases we can consider here. So why can't we just take alpha as big as we want, right? If Cj is negative, that means increasing xj. If C bar j is negative, that means increasing xj by alpha, setting it equal to alpha, will decrease my objective. So why don't I just keep doing that forever, right? I just more and more decrease, right? So actually, what will happen? I haven't been asking that many questions. What will happen if I do that? Yeah.
At some point, your x will no longer be greater than 0.
Exactly, right. So in the case, actually, where this term here is all positive, you're actually good in some sense, because the other x's are changing exactly by this amount, right? The other x's are changing by alpha times di. So if they're all, if we're in the lucky case, I think lucky is, again, a little bit in quotes here. If we're in the lucky case that all the di's are positive, then we actually can just keep on going forever. Because when we change xi, it will never have any term go negative. We can just keep decreasing our function forever. And what really is happening there is we have an unbounded problem. However, if any single element of di is negative, then you're exactly right. Sorry, what was your name? Michael. Then Michael's right. So then what's going to happen is, at some point, for a big enough step alpha, this term, one of these terms is going to turn negative. And then that's no longer a feasible solution if we just keep going further and further, right? It's no longer a point on the corner of a polytope or in the polytope. So we can't go on forever. So for any single coordinate here, so let's think of an xi gets the value of xi plus alpha di. This is for the ones that are in my set already. So for that one, the biggest step I can take before that one becomes 0 would just be alpha. So this thing is set equal to 0. So that means alpha equals negative xi over di. Right? So if I want to make that coordinate 0 and the di is in fact negative, I should take a step that's that size. So what I'm going to do is I'm going to take as big a step as I can until one of my existing xi's becomes negative or really hits the 0. Hits 0, right? So I'm going to find the alpha here such that the first one of my xi's, when I update it, becomes 0. And kind of the formula, the way I do that, remember, these are my step sizes here. So what I do is I find the I star, which is the argmin of I in my index set, such that di is negative, of this thing, xi over di. So I actually don't even care what this term is. I don't care what the step size is. I just care which component is going to hit first. I'm going to take that size. Yeah, there's a question over there. The question is, can you have different step sizes? So you always want to take as big a step size as you can in order to hit your point. Right? Because if I take a too small a step size, what I'm doing is I'm not moving all the way to a corner. I'm kind of stuck in between these two things. And there's no reason to take a smaller step size than the biggest one I can take. I can't go any bigger than this. Right? I can't go any bigger than this for x star, because then I'm no longer feasible. But if I go less than that, there's no advantage. Right? I'm just not decreasing my function as much as I could. So there's no point. So what I'm going to do is I'm going to find the biggest step size I can take. But really, I'm just finding which is the coordinate that when I take that step would hit 0 first. And what I do then is I just update my index to take off that point, and I add j. Right? Because now x star I, we know, it becomes 0. So it leaves a set of points. It's just one of the sets of points that's 0. And we add xj to our index set now. So we add j to our index set. In other words, xj is non-zero. And we repeat that process. That's it. So here's a simplex algorithm. The first isn't really a procedure. The first is just, in fact, a statement. But we're given some index set I such that this condition holds. In other words, this is a feasible point on our polytope. We find some j for which this term, this decreased term, is negative. Yeah, question there? J is always out. Sorry, I should say that J is outside the index set. So find J not in I. Yeah.
Essentially, you're pushing something in the index set to 0 and then pushing something in the index set.
Yeah, exactly. You're taking out one element, the one that goes to 0, and you're adding a new element. So I'm finding a J, which when I take a step in that direction, I know that I, in fact, decrease my objective. It would be a bad idea to take any other way. It turns out, as long as you can find one that does decrease, doesn't really matter which one it is. You can take kind of any of them. Then I find, the index of the current point in my index set that will hit 0 first, and I just update my index. Now, one thing that is cool here is I don't even have an alpha in this algorithm, right? It's implicit in this term right here. That is the alpha, but I don't actually need to compute. I don't need to, adjust my x by it. I just effectively add an element to my index set, take one out, and by doing so, I've actually moved from one point on the one corner of the polytope to another corner. And that's the simplex algorithm. I have one poll, but I'm actually, before I do the poll, I want to just have this I want to make sure I get through this theorem first. And the poll, people are keeping themselves here if they don't answer the poll then. Because I have to also create it while I do that. So the very cool theorem now is what we can say really, really quickly is that the simplex algorithm will solve a linear program. I'm actually avoiding a couple things like degeneracy or things that, basically where it's constraints that can actually both be active at the same time or in the same point. There are edge cases here. So this is not really a rigorous proof here. But the intuition here is actually very simple and it's correct. And it's very simple because we already know about convexity. So what the simplex algorithm does is it finds a point where we can't get any lower locally. Right? So we look all around. We can't make a local change to our vector x that decreases our objective without violating our constraints. Okay? So it is, in other words, it is a local optimum for our problem. And we know, because this problem is convex, a local optimum means this is the global optimum of the problem. So we proved last time. And, and therefore now we can say in one line, we can say that we have found the global optimum of the problem. The other question is why this thing will ever terminate, though. I mean, it might never stop, right? And the reason why it does stop is because at every step, we know the objective has to decrease, right? We know at every step we take, the objective is, in fact, decreasing. And we know there are only a finite number of points, of corner points on this polytope. It can be very big, but it is finite, right? And so therefore, the algorithm has to terminate after a fixed amount of time, or after some finite time. And when it terminates, it's found the optimum, or it's found that it's an unbounded problem, etc. And so that's the very, very simple proof that only possible because we know it isn't that complex if you don't know convexity. But with convexity, it's a very, very simple proof that the simplex does in fact work. So let me ask one question now. I'll add a poll here, and I'll see if I can add it really quickly. What's the complexity of the simplex algorithm? Of a single, I should say, we know is exponential and that it can take an exponential number of iterations. What's the complexity of a single iteration? Let me open up my poll here. Again, I'm going to create one. It's just going to have 4 options. Where's my cursor? Huh. I should have put an exponential one in there. I should have put wouldn't be very useful if each iteration was exponentially complex. But okay, so sorry. So complexity of simplex. 1, 2, 3. I had such nice LaTeX in my answers and everything for the actual one. So apologies for that. Okay, so people can see it now. So we're almost out of time, so I would recommend everyone just vote. I think everyone's voted, so that's good. Okay. Wait, no. Where's complexity of simplex? Okay. Okay. All right. I'm going to close it now, and we'll just discuss. I'll just say what the answer is, and then you can try to prove why it is the case. So really even. So maybe people just try to get out of here and like randomly guess one of those. So I'll humor you guys and just let you do that. But the answers, if you care, are 3 or 5, depending on how you implement it. So go and think about why that is. All right.